Assalamu alaikum. We want in this part to determine the characteristics of a magnetic field created at the center of a flat coil and to determine the characteristics of a magnetic field created inside a solenoid carrying current. There is another case for magnetic field created by a circular wire, which is case of a flat coil. First, what is the flat coil? A flat coil is made up of n circular identical loops, where its thickness L is negligible relative to its radius. Look to the following figure. This is the flat coil. These are the circular loops. They are identical. Each loop has radius R, and the thickness of the flat coil is L. L is much smaller than the radius R. Now we will talk about the characteristics of the magnetic field at the center of a flat coil having N loops. 1. Origin. Its origin at the center of the coil. 2. Line of action. It is perpendicular to the plane of the coil. 3. The direction is indicated by the right hand rule, as shown in the following figures. Let's start with the first drawing. If you curl your fingers of your right hand in the direction of the current, you will notice that your thumb is directed to the left in this example. So the direction of the magnetic field is to the left, and it is perpendicular to the plane of the coil and at the center of the coil. In the second example, if you curl your fingers in the direction of the current, you find that your thumb directed to the right. Then the direction of the magnetic field is to the right, and it is also perpendicular to the plane of the coil, and it is at the center of the coil. Finally, magnitude. We can find the magnitude of the magnetic field by applying the following rule: mu0 Ni over 2r. You know the value of mu0, which is permeability of a free space, and is the current, or is the radius of a loop, and is the number of loops. Note that since the flat coil makes up of many circular loops, we find that the magnetic field created at the center of the coil and the magnetic field created at the center of the circular loop have the same characteristics, except the magnitude, where the magnitude of the flat coil is mu0 Ni over 2r, whereas the magnitude of the circular loop is mu0 I over 2r. So just the exception is the number of loops. We can say that the magnetic field of the flat coil is equal to N multiplied by the magnetic field of the circular loop. To clarify the idea, let's watch this video. Sprinkle some iron filings on the cardboard irregularly to be randomly distributed. So what happens when a current traverses this coil? When we apply a current to the coil, then it generates a magnetic field. And what will happen is that the iron filings will be magnetized and rotate around the magnetic field lines. So we can visualize the generated magnetic field lines. Now turn on the current. As you observe in this video, the iron filings are redistributed. Look here. Inside the coil, you can clearly see how the iron filings have rotated along the magnetic field lines. And as we move away from the coil, you can see how those field lines start to spread out. Last objective for this part: magnetic field created by a rectilinear solenoid. What is the solenoid? A solenoid is a helical winding of wire where its length is larger than its radius. This is a solenoid, this is the radius of the solenoid, and this is its length. As you notice, the length of a solenoid is much greater than its radius. It's important to know that the magnetic field created inside the solenoid is directed according to the right-hand rule. The line of action of this magnetic field is the axis of the solenoid. Its magnitude can be calculated by applying the following rule. B equal mu 0 capital N I over L, where L is the length of the solenoid and N is the number of loops. We can also use the following rule. B equal mu 0 small n multiplied by the current I, where N is the number of loops, N equal capital N over L. The magnetic field inside the solenoid is uniform. That means all the magnetic field lines inside the solenoid are parallel to each other and have the same magnitude. As you see in the following figure, this face of the solenoid acts as south pole and this face of the solenoid acts as the north pole. And according to the right-hand rule, the magnetic field is directed to the left. So it is directed from the south pole to the north pole. To clarify this idea, let's watch this video. I'm now going to sprinkle on some iron filings into the plastic sheet. The iron filings are randomly oriented. When I apply a current to the coil, a magnetic field will be generated. This magnetic field will magnetize the iron filings and they will rotate and align along this magnetic field. So now I'm going to apply a current. Inside the solenoid, you can see clearly how the iron filings have rotated and aligned along the magnetic field lines. Now let's zoom in on this. So you can see how they align along the axis of the coil. These lines are parallel to each other. Because of this spreading, the field outside the coil is extremely weak compared to the field inside the coil. Application. Calculate the magnitude of the magnetic field inside a 2-meter long solenoid and that has 2000 loops and carries 16 ampere current. So we want to find the magnitude of the magnetic field. We have the value of the length 2 meter, value of the number of loops and 2000 loops, the value of the current 16 ampere. So just apply the following rule. B equal mu 0 N I over L. Mu 0 is 4 pi times 10 to the power minus 7. N 2000 loops. I 16 ampere. L 2 meter. As you notice, these values are expressed in their SI unit. So we get the value of the magnetic field B 0.0201 Tesla. Part 2. For the same application, calculate N, small n, the number of the loops per meter, then deduce the magnitude of the magnetic field. So first we want to find N, then deduce the value of magnetic field. And by applying the rule capital N over L, 2000 over 2, we get a small n equal 1000 loops per meter. Now, to deduce the value of the magnetic field, we use this formula B equal mu 0 Ni, where N is the number of loops per meter. Substitute the values to get the value of the magnetic field 0.0201 Tesla. So, as you notice, we have two methods to find the value of the magnetic field, and we get the same answer. This is the end of the first part. Determination the characteristics of the magnetic field created by a flat coil and that created by a solenoid. Thank you for your attention and good luck.